Alright, so we looked at the race condition, right? So, and while talking about race condition, I told you this happens when multiple processes are modifying the same data. So, if you have 10 processes and all of them are reading from the same register or same variable, there is no problem. You all can read in any sequence you want and it's going to be the same value. But when you are going to write onto that place, when one or more people are writing onto that location, is when the problem or the challenging situation comes into play, right? So we can say that writing or any part of a program where a data member is being modified or written on or updated or deleted is a critical section, because in that section you need to handle it with care, otherwise you might end up with a race condition. Whereas the part of the program where you're simply reading or accessing can be called the remainder section. That you can be a little carefree about it. You don't need to care too much about the order or anything, because that is not going to affect your problem. So I define critical section as the segments of any program or process which are going to make changes to a data entity, and remainder section as those segments which only access and read your data but do not make any changes. So if you want to prevent your race condition, the idea is at any given point of time, at most one process should be allowed to execute its critical section. The remainder section of multiple processes can run at the same time. So remainder section in loose terms is the reading parts. So 10 processes can read a data location at the same time and they will all get the same value, and the value in the location is not going to change. But if 10 processes are going to write at the same time, depending on the sequence in which they write, you will end up with different final answers, which is what we saw as a race condition. So the remainder section of any number of processes can be executed concurrently, but the critical section of 2 or more processes which deal with the same data, same variable, should not run concurrently. If you have more than one process which works with the same piece of data, at most one of them should be allowed to execute their critical section at a time. So that once this one has finished writing, only then the next one writes. So it almost becomes like a serial execution. So if you look at if you remember your increment decrement example from the previous, whether you do 1 followed by 2 or 2 followed by 1, because it becomes a serial thing, your final answer is going to be 5 in both cases. So that is what we want to ensure here, by making sure that the critical section of at most one process is executed at a time. So this, how do you ensure this, is what we call the critical section problem. So I'll state the problem formally. The critical section problem is to design a protocol that the processes can use to synchronize their activity so as to cooperatively share data. What is this technical sentence telling us? You have to design a system such that a system which ensures that at any given point of time, at most one process is executing its critical section. Remainder section, any number of processes can execute. How do you design a system which enforces these rules? That is the critical section problem. So before we look at solutions to the problem, we'll see what are the constraints the problem must satisfy. So I said the problem is how do you define a system which makes sure at most one critical section is executed, right? So when you design a system, what are some requirements from this system? Mutual exclusion. If PI is executing its critical section, no other process can be executing its critical section. This is exactly what I mentioned. Note that we are looking at processes which work with the same data. If 2 processes are dealing with different data sets, then they are free to run parallelly. There are no problem is going to come up. If 2 or more processes are working with the same data, and if one of them is executing the critical section, the others must not be allowed. That is the mutual exclusion condition. Next is progress. If no process is executing the critical section and one process wants to enter, then it should be allowed to enter and you cannot indefinitely make it white. So when someone is executing their critical section, you will have to make the others wait. But if no one is executing their critical section and someone comes and says they want to execute theirs, you have to allow them immediately. In such a case, you will not make a process wait. That is the progress condition. And third is bounded wait. So I said when someone is executing their critical section, the others wait, right? So this wait should not be indefinite. Once the process PI has finished its critical section, the next ones which are waiting should be allowed. So PI should not be sitting there in critical section mode all the time, and the others should not be left to wait indefinitely. So once one process has finished its execution of the critical section, it should come out, it should deal with the remainder section, and the next process which was waiting should be admitted into the critical section execution. So quickly recap, what are the constraints? What is the critical section problem? First of all, you define or you design some security enforcement technique which makes sure that at most one process executes its critical section at any given point of time from a bunch of processes dealing with the same data. If no one is executing their critical section and one process comes in saying it wants to, it should be allowed to immediately. And if one process is executing its critical section and the others are waiting, after a period of time, this process should stop, come out, and the others one by one should be let in. No process should have to wait indefinitely. So keeping these three in mind, we are going to see how we can design a system which, and by system I just mean a set of rules, some logical framework that makes sure that all of these constraints are met. So that is the critical section problem, and in the forthcoming segments we will look at a couple of solutions to it.